Welcome to Session 5 of Digital Basics, a negative turn. As always, we begin by reviewing the answers from last session's exercises. We need to create a truth table based on this configuration of gates. We'll begin with out 1. We could go through one truth table line at a time, but we can speed things up a bit by taking a moment to look for aspects of the logic that may affect multiple combinations. For example, when input A is 0, the output of the OR gate is 1, regardless of the state of input B, which leaves us with input C. And we see that input C is XORed with the 1 out of the OR gate. So we know that out 1 is the inverse of input C. That's a property of XOR gates. A 1 applied to one input makes the XOR an inverter for the other input, more or less a controllable inverter, if you think about it. We now need to see what happens when input A is 1. Because of the inversion at the input of the OR gate, when input A is 1, it's all up to the other two inputs. Input B passes straight through the OR gate, so it's just an XOR of input B and input C. Like so. Moving on to the second output, out 2. We begin by again looking for conditions that determine multiple rows at a time. And we find right off the bat that when input A is 1, then both inputs of the XOR are 1, and therefore the output is 0. We next recognize that the only combination that produces a 1 from the AND gate is 1, 0 for input B and input C. This results in a 1 for output 2. Since input A is 0, and that presents a 0 and a 1 at the XOR. We now know that all the other combinations of input B and input C present a 0 at the XOR. And so, out 1 is 0 for those as well. For the next exercise, we're asked to do the reverse, to create gates that implement a provided truth table. There are any number of gate combinations that correctly implement this table, and we'll explore just one. As usual, we look for general patterns, and we notice that the output is 0 when in2 is 1. This sort of implies an OR gate. But that doesn't work, since the output is opposite that of in2. We would need to add an inverter. We could show this as an inverting bubble on the OR output. In fact, this is its own type of gate that we call a NOR gate, a contraction of not OR. Also, the AND gate has its own version that we call a NAND, not AND. But back to our table. We next notice something somewhat familiar about the first half. It looks sort of like an XOR, except we would expect that when the inputs are the same, we would get a 0. But this is a 1 output. And when the inputs are opposite, we should get a 1, but this is a 0 output. It looks like an XOR whose output has been inverted. And sure enough, there's the inversion. And since N2 is low for these table entries, it has no contribution through the NOR. So there's our answer. And finally, the last exercise has us working with hierarchical blocks. We first look at the table entries with the enable active, noting that this enable is shared across all 3 blocks. With an active enable, we see that the block is just an XOR gate. Since the carry-in of the first block is tied to 0, sig 0 passes straight through, and sig 0 appears directly at the first block's output. So the second block's output is therefore the XOR of sig 0 and sig 1. And that result is then XORed with the last sig 2 to produce the final output, which leaves the last table row where the enable is now 0. And since that gates off both inputs of each block, the output is 0. We've already learned how to add binary numbers. But what about subtraction? We'll get there soon, but we need to set the stage with a couple of steps. And the first step is to introduce the idea of ones complement binary numbers. Let's start with a binary 5 value. We convert that to a ones complement by simply inverting each bit. A ones complement is considered a negative version of the original number, and we use the ms bit to indicate this, with a 0 indicating a positive value and a 1 defining a negative. Note that by using the ms bit as a sign bit, we give up 1 bit position. Ones complement values, however, are simply a first step to where we need to go, which are 2's complement numbers. And to create these, we simply add a 1 to the ones complement. Note that the ms bit is still the sign bit indication. So, in summary, to create a 2's complement binary number, we simply invert the positive number and add 1. What's the point, you might well ask? Well, as we'll now see, there is some arithmetic magic inherent in 2's complement numbers. Let's take a number, say again 5. And we'd like to subtract 2. We begin by taking the 2's complement of the subtrahend, the 2. We add the 1 to that to get its 2's complement. Here comes the magic. Instead of the original binary 2 that we want to subtract, we add the 2's complement. And I'll repeat that just to make sure you get the important point. We add the 2's complement. You see, we know how to add binary numbers. And when we do, we get, magically, the correct answer. When we added the 2's complement number, you may have noticed that we had a 1 that carried out from the last binary bit. We just throw that away. It's an artifact of the math magic. So we have a method to both add and subtract binary numbers, where subtraction includes creating both a 1's complement and 2's complement of the subtrahend, which we already know how to do with logic. But what if the subtrahend is the larger, like this example where we want to subtract 5 from 2? Let's go about it the only way we know, creating the 1's complement, and then the 2's complement, and adding that to 2. The result is a binary 1, 1, 0, 1. We recall, though, that the ms bit of the 2's complement is a sign bit, where here it indicates that the 2's complement is negative, perfect for subtraction. Well, that sign bit applies here as well. If we do a 1's complement, 2's complement conversion, we find that we get a positive 3, which is our answer. The important point here is that we've chosen to use 2's complement numbering, where the ms bit indicates whether the number is positive when 0 or negative when 1, in which case the rest of the number is in 2's complement form. Before leaving 2's complement numbers, let's look at what happens when we're given negative numbers to start with. Here, we're adding a negative 2 to a negative 4. Here's our negative 2. We can confirm this by taking the 2's complement, remembering that the conversion works both ways, positive to negative and negative to positive. Noting the two versions. Next, we bring in the negative 4, again confirming by taking the 2's complement. And finally, we do the addition. We use 2's complement conversion and confirm that the answer is a negative 6, as expected. Although the 2's complement form of negative binary numbers is the most common for operations that include arithmetic, like what's going on right now in whatever device you're using to watch this, a simpler method is to carry both positive and negative numbers as positive, and simply indicate if it's positive or negative, using the ms bit as the sign indicator. This is called sign magnitude, where a 0 indicates a positive number and a 1 a negative number. And finally, the exercises for this session.